Hello there, and welcome back to Nature and Code. We're in chapter 3, and we have in the past few videos developed an intuition for randomness. And we found a way to implement randomness in code. And in JavaScript, that implementation is mathrandom, and we'll use that method many times. Just to recap, mathrandom generates a random number between 0 and 1. And that's going to come in very handy. In future videos and future code that we'll develop. So let's go back to biology. So in the earlier videos for chapter 2, we learned about the Hardy-Weinberg principle. And as you may recall, we always looked at this example of two possible alleles, A1 and A2, and we denoted the frequency of the A1 allele as P, and the frequency of the A2 allele as Q. And then we said, all right, so now let's generate our next generation, and we would pick alleles according to their frequencies, P and Q, and we would do this infinitely many times to create the new generation of an infinite size. And if we do this, nothing changes here in the allele frequencies. And we will get these Hardy-Weinberg frequencies for the genotypes. So A1A1 would be Q times Q, and the A1A2 would be 2PQ, and A2A2 would be Q times Q. So that was Hardy-Weinberg. And as I said earlier in the beginning of chapter 3, we're now going to relax this assumption of an infinite size. Okay, so no more infinite population size. Indeed, we will have now population size of n. Okay, so that is the variable that we'll use to denote the population size. So n will be the population size, and since we're talking about diploid individuals, we will have 2n alleles in the population. And now things will change quite dramatically, and I hope that you have now a little bit of an intuition of why that is. So what we are now going to do is we're going to keep all these assumptions, but instead of creating infinitely many new genotypes, instead of picking infinitely many alleles, we are now only going to pick 2n alleles for the next generation. We are still going to assume then that this next generation will produce infinitely many gametes, but there will always only be a finite number of individuals, okay, and that is n. And so this is now quite similar, or in fact more or less identical, to the coin tossing example that we developed earlier on. So as you may recall, we had an example where we said, okay, we have a fair coin, heads comes up 50% of the time, tails comes up 50% of the time, and so now we're going to flip the coin, say 10 times. That was our example, and we'll get, sometimes we get 5 heads and 5 tails, but oftentimes you get 3 heads, 7 tails, or even 2 heads, 7 tails. And in fact, we even calculated the probability that we get exactly 2 tails and 8 heads, or 2 heads and 8 tails, which is the same probability. And that probability was between 4 and 5%. So it's not unusual to get a situation where you have only 2 of one side and 8 of the other side. So now this is exactly identical to the situation where we would have P equals Q. So both alleles now at 50%. And now let's say we would have a very small population, admittedly very small, of 5 individuals. Okay, that's our population size, which means we would have to pick 10 alleles, right, 2n alleles, to create 5 new individuals, 5 new diploid individuals for the next generation. And that's now the exact same situation. So I could just draw here these 10 positions, and now rather than having throwing coins and having H and T's, I'm basically picking alleles, and I now get something like this: A1, A2, A1, maybe an A1 here, maybe, and so on. And so, it's very easy to see that this is the exact same situation with H and T, and we can very easily end up in a situation where the frequency of the A1 allele is now not 50% anymore. And the frequency of the Q of the A2 allele is also not 50% anymore. So to bring this point home, I actually want to, sort of run a simulation here with you. So let's say, let's assume a population of 10 individuals. Again, this is very small, but just to make the point, which means we'll have 20 alleles in each generation. These individuals then will create an infinitely sized gamete pool. Okay, so that's our infinitely sized gamete pool here, and so we have lots of A1s and A2s. And in fact, we'll start with the assumption that the A1 allele is as frequent as the A2 allele, which means they're both 50%. And so I could, of course, go on here all day and draw A1s and A2s. But here, that's the important point, right? So now I'm going to create the next generation. What does that mean? So that means I have to pick 2n alleles. And at this point, I'm actually not going to care exactly what sort of new individual genotypes we are going to produce. We just care about the number of alleles, the number of A1 and A2 alleles that we pick here. I just care about the allele frequencies for the time being. So I'm going to set up a counter here for A1, and I'm going to set up a counter here for A2. So now I'm going to go over to the browser and I'm going to ask Google here to help me flip a coin. And here it is. So if you Google flip a coin, Google will give you this nice little tool here where you can flip a fair coin whenever you click on this link. And so I'm going to say heads is A1, and it corresponds to an A1, and tails corresponds to an A2. So let me start doing this, okay? So let me flip this, and this will be picking the first allele. Okay, so this comes up heads. All right, so we have one A1 allele. All right, let me flip this again. Tails, okay, we have an A2. Flip this again. Heads. Flip it again. Tails. So I have to do this 20 times. So I apologize if this is a little boring, but it serves a purpose. Okay, heads. All right, heads again. Tails. And heads. All right. Tails. Heads. So in fact, if we would stop here, I've picked 10 alleles. If our population size were 5, then you could already see we already are at an unequal A1, A2 ratio, right? We would have 60% A1 alleles and 50% A2 alleles. But let's continue for another 10 times. So, tails. Tails. Heads. 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 All right, I got 16, so 4 more. Heads. So this is a fair coin. Heads. Wow. Okay. Tails. And one more. Heads. All right, so the tally is 13 and 7 here. Okay, so this is now our new generation. Our new generation has 13 A1 alleles out of 20, which is 65%. And our population has 7 A2 alleles out of 20, which corresponds to 35%. And that is, of course, now our new P, and that is our new Q. And let's just think about what happened here. We started with allele frequencies P and Q 0.5. Remember, in the Hardy-Weinberg, this is the case in all eternity. The allele frequencies will never change. This was our null model. This is why the Hardy-Weinberg world is so boring, because nothing ever changes. The allele frequencies don't change. And remember, that is the definition of evolution. It's the change in allele frequencies in a population over time. And we established that this wouldn't change, not the slightest bit. Now, here in one single generation, we had this dramatic change from 50-50 to 65% and 35%. In one generation, a dramatic change in allele frequencies, which means a dramatic evolutionary change in a single generation. And the only thing that is now different from the Hardy-Weinberg world is that we have a finite population size. So this is the key aspect. A finite population size means that we're now sampling alleles in a finite way. We're just picking a few alleles, however many we have to given n. And that means we'll introduce a random process and the random effect of sampling. And so, as you can see here, in small populations, this process can lead to very substantial changes in the allele frequencies in a very short time, in a single generation. And that is called genetic drift. And so I want to stop this video here and in the next video move over to implementing this idea in JavaScript, because then we can investigate the effect of this population size on this process. I'll see you in the next video.